Okay, so here for a while I want us to consider the main concept around tilting. Up to now, we've really modelled weights being in between two pivot points, whether these are two supports below or it's two strings from above. But the weight's been in between. The distance of the weight from the pivot points has an effect on the reaction forces. But we want to consider what effect will it have if the weight was outside, on the outside of the two support points. So not in between them, but over here, let's say to the left. Well, in this case, there's the potential for the system to lose its equilibrium. There's the potential for the beam to tilt. This would come down to multiple variables, from the length of the rod to the distances between the support points, the distance to the particle or the weight, the actual weight of the rod itself. There's multiple variables that will be included in whether or not this would happen, but we'll be interested in the instances where it does. If it was going to tilt, it will tilt around the nearest support point, so it will be tilting around A. What happened to the actual reaction forces? Well, as it's about to start tilting, so this is all going to happen instantaneously, the reaction force at support A is going to increase, while the reaction force at support B is going to reduce. So one of them is increasing while the other is decreasing. The resultant of the reaction forces, the total of the reaction forces, will remain the same, meaning that all of the reaction force is going to be present at A. However, right at the point where the beam is about to start tilting, the reaction force at support B is 0. The reaction force there is nothing. The reaction force no longer exists. It's about to lift off of the support point. The beam is about to move up and away from being in contact with the support. So there is no reaction force anymore. There's not even any contact. And it's the contact that actually produces the reaction force. So the fundamental point here is that when we're modeling the exact point when tilting is going to occur, we realize the reaction force in the second support must equal 0. We model it to equal 0. As long as we can include that in our model, we will have the correct model to go ahead and find any unknown values and to confidently problem solve while we know that this system, this plank, this rod is about to tilt. So let's have a go at an example. Here we see that we have a uniform beam AB. Its mass is 45 kilograms, length 16 meters. It's resting horizontally on two supports C and D. We've got some distances in here, and we're told that when a child stands at A, the beam is on the point of tilting about C. So let's go ahead with the diagram as usual. We know it's uniform, so we can straight away put the weight right in the middle. So 45G. 16 meter rod or 16 meter beam means that A to the middle is going to be 8 meters. We know that the support C is actually 5 meters away, so I can label 5 and then 3 to get to the middle. We know that support D, there's a distance of 9 meters from C to D, so I've got the 3 to the center, another 6 will get me to D, and then I've got 2 meters over there. Fully labeled each of the individual lengths. Let's see what's missing from the model. Okay, we're going to model the child and their weight. So the unknown mass multiplied by G, I'm going to use that to represent this unknown weight of the child. We were told that this system is going to tilt around C, which means that there's no reaction force at D. So I don't even need to model anything at D. Let's just get this reaction force at C, and I think the diagram's finished. We'll use our usual strategies. So I'm going to start by resolving vertically. I know that that reaction force is going to equal the two downwards forces. So that will be the weight of the beam and the weight of the child. So R is going to equal, if I factorize, 45 plus M multiplied by G. Second strategy that we always use is to take moments, and I'm going to take moments from C, and that's the only sensible place to take moments from here, because it means I don't actually even need to use the reaction force, because that is going through the point C. So I'm going to go ahead and get my clockwise moment, which is generated by the weight of the beam itself, and the anti-clockwise moment, which is generated by the weight of the child. Hopefully you can see where we're going. We're just going to expand, rearrange, simplify, and I should get an expression for this unknown mass of the child. So M equals 130 over 5. I've just cancelled out the G straight away, and that gives us 27. So the mass of the child, 27 kilograms. So as usual, just interpreting the context to produce a good, well-labeled diagram, and from the diagram applying our two strategies of resolving vertically and taking moments from a sensible spot. Okay, so let's have a look at another one. This time it's been suspended from a pair of light cables, and we want to make sure we demonstrate this in the diagram. So a non-uniform rod, AB, of length 10 meters and weight 40 newtons, is suspended by two cables C and D. AC is 3 meters, so I'm going to add that to the diagram straight away, and BD is going to be 2 meters, so that's at the other end. I know that that's going to be 2 meters. Add that to the diagram. It's a non-uniform rod, so I don't actually know where I should model the weight of the rods. But I'm going to assume for now it's in between C and D. I know that there should be 5 meters in between C and D, since it's a 10 meter rod. So I'm going to label this length here between C and the center of mass. I'm happy to call that X. And then between the center of mass and D, I'm going to call that 5 minus X. So two ways to represent these unknown lengths. So in the text, we were told that the rod is at the point of rotating, another word that they might use instead of tilting. It's at the point of rotating around point C. So we actually know that there's not going to be a reaction force at D. So you can label this as 0. I'm just going to get rid of it for now. Okay, we should have probably modeled this earlier. Let's put on that weight, that 25 Newton weight at point A. Diagram's complete. We can go ahead and employ the strategies we usually do. Let's take moments around C. So anti-clockwise, we've got the 3 times the 25 newtons, and clockwise, we've got that unknown distance multiplied by 40. Expand, rearrange, simplify. We get an answer for X, which says that X is 75 over 40. As a decimal, we'll take that as 1.875. So the distance of X is 1.875 meters. The question actually asked us how far away from A. So we need to add on the 3 meters that we already have, and that gives us a final answer of 3.875. Okay, so once again, interpret the text to produce a good diagram. From the diagram, we had to do a little bit of labeling of the unknowns, the X and the 5 minus X. I hope you're getting used to that kind of technique. But once again, from the diagram, we employed those two strategies, resolving, taking moments, and that helped us to find the unknown.